Today is scheduled to be a review day for my chapter 16, but in your text it'll be, in your textbook it'll be, that is Brown, will be section 17.4 to 17.7. What that tells me is that Brown doesn't consider it very important to only put 3 sections in their book. Actually 4 sections for such an important topic. And if you've dug into the review documents in Blackboard, you'll find that it's a good thing that we limited exposure to this topic for one exam, because I hope to show the different types of problems that can arise from solubility and complex ion studies. So what I'll do now is I'm going to share one of the review document keys. I had broken the review documents into 2 versions because a single version just had too many problems in it. So I split them into roughly equal sized documents, and each document has the same spread of different types of problems. So if you've only got time to do one, you'll be fine. So let me share this document right here. There we go. Let me make it a little bit bigger. There. Okay. So I've picked out several problems. I hope I have time to finish them all. I counted them up. There are 25 or so of these questions that I want to look at. We'll do the best we can. Okay. So we're going to start with number 5. All right. Barium carbonate has a measured solubility of 4.03 times 10 to the minus 5. And that you can assume that if there are no units given, the solubility is in terms of molarity. This molarity at 25 degrees Celsius. And the question is, determine the KSP, the solubility product. All right, so barium carbonate is what? We need to know the formula in order to set up the solubility equation. Barium and then carbonate. Okay, is that written correctly? Well, we'll look, where is barium? Barium is an alkaline earth, so it's 2+ charge. And carbonate is a 2- charge. So yes, it is written correctly, just like that. That's a solid, and it's going to be in equilibrium with its ions in aqueous solution. Like that. Okay, let me be sure that's on screen there. There we go. Okay, so we need to know that in order to write the solubility product. So KSP is going to be barium to the first power and carbonate to the first power. Okay. And we're given the solubility, though. The solubility, and I think the textbook tends toward using S for solubility. So S is our solubility at 4.03 times 10 to the minus 5 molar. Okay, what does that mean? That means a second. Keep myself straight here. Yeah. That means that at equilibrium, this many moles per liter of that goes into solution. So at equilibrium, how much of this do you have? Well, you got one of these and one of those. So you have one of these, this much. You also have the same amount of that much. So the solubility product would just be this one, and we may write it in these terms. S squared, because it's S times S. So if we square this value, we'll get the KSP. So let me square that value and see what we get. 4.03 exponent 5, change sign, enter, and then square it. 1.62 times 10 to the minus 9. Okay, is that one of our answers? Yes, E is the answer. Okay, that was simple enough. It's also a good point to make here that when you are given the solubility, or when you're devising a formula that is equal to your K value, you look at the balanced equation and you say, what does S mean? If S is the solubility of this, then that's equal to S. And then you say, now what does that mean in terms of the ions in solution? So in this case, S here is equal to S there and S there. But in more complicated dissolutions, the S's can mean several things. And we're probably going to encounter those in just a few minutes. So I'm going to mark these off as I go in case I have to skip one and come back, because I don't want to get too complicated early on. I'm going to do the easy ones first. 6 looks like a good candidate. Here we go. All right. All right, so 6 says what? The correct mathematical expression for finding the molar solubility, S, of 10,2 hydroxide is what? Well, start off with 10,2 hydroxide. And what is it going to give you? Well, that's equilibrium. It's going to give you a 10,2 plus ion plus 2 hydroxyls. Right? So if the solubility of this is S, then this is going to be S. And in terms of our ice table, this will be, you'd lose that much, and you'd end up with this much here, but you'd also end up with 2 S's over there. Okay? So now what's the KSP is equal to what? Because if you know the KSP, then you can solve for the solubility. The KSP then would be equal to that. Let's just be methodical about it. To the first power, and this one to the second power. Now if we put S in here and 2S in here, squared, right? We get 2 squared is 4, and S squared times S is S cubed. So KSP should equal 4S cubed, right there. Then if you're given this value, that value, you can solve for S because it's the only unknown in that equation. Okay, that's number 6. Let's see what's next on the agenda. How about number 11? There's number 11. All right. Let's see, am I still on target here? There we go. Number 11. All right. Which of the following compounds has the lowest solubility in moles per liter or molarity in water? Which one has the lowest solubility? So that means we've got to calculate each one. And why is that? Well, if each one produced the same number of ions, like if they were all like cadmium sulfide, 2 ions each, 2 ions, 2 ions, then we could directly compare the KSPs and say which one has the lowest solubility. But they don't. They each have different numbers of ions that are produced from the solubilization of each one. So that means we have to actually calculate the solubility for each one in order to determine its, in order to compare the solubilities. Okay. All right. So what we need to do is be very methodical. In other words, here comes Henry Ford. We're going to make a assembly line out of this thing. So we've got the first one is silver phosphate. Okay, I'm going to move this up here. Silver phosphate. Right. The next one, let's see, this is A. Next one is 10,2 hydroxide. C is cadmium sulfide. And calcium sulfate is D. And E is aluminum hydroxide. Okay. So what do these things produce when they're at equilibrium? They produce 3 silvers and 1 phosphate. Right. This one produces 1 tin and 2 hydroxyls. This one produces 1 cadmium and 1 sulfide. So this is 2 plus, and this is 2 plus and 2 minus. Okay. This is calcium, 2 plus, and sulfate, 2 minus. And this one is aluminum, 3 plus, and 3 hydroxyls. Okay? So, if we lose S for each one of these, right, what does that mean that we're going to get over here? Well, the KSP for each one, let's just write the KSP values down. 1.8 times 10 to the minus 18. and then 3 times 10 to the minus 27. Next, 1 times 10 to the minus 28. And then 6.1 times 10 to the minus 5. And then 2 times 10 to the minus 33. Yep, 33. So these are going to be equal to the equilibrium values for each one of these with its proper assignment. If this is S, then this is going to be S. I'm going to look at each one that has a 1 coefficient. If it has 1 coefficient, it's going to be S. S, 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 S. And this one's going to be 3S. This one's going to be 2S. I probably should have used a different color for those. Well, it's too late now. 1, 2S here. SS. This is going to be 3S. Okay? So now, on this side, we have that one times that one with the power of the coefficient. So this one's going to be 3S to the 3rd power times S. This one's going to be S to the 1st power and 2S squared. This one's going to be S and S. This one's going to be also S and S. This one's going to be S and then 3S to the 3rd power. Okay? So now we have this unknown equal to that one each time. We just need to solve for each one. Okay? So what would this one be? 3 cubed is 27. S cubed, 27S cubed times S is 27S to the 4th. This one is 2 squared, which would be 4S squared times S is 4S cubed. This one is the S squared. This one is the S squared. And this one is same as that one. Okay? Now, if we solve for S in each one of these cases, I kind of run out of room. But all you have to do is solve for the S in each one of these. Right? And I'm assuming you know how to do that. In fact, well, okay. We've already used this information, so I'm going to erase this and do the calculations over here on this side. All right. So this one would be 27 divided into that would be equal to S to the 4th. Correct? 1.8 exponent 18, change sign, divided by 27. Well, that's not right. Let me do that again. There we go. 6.67 times 10 to the minus 20. Now we just need to take the 4th root of both sides. In your calculator, you may have a root key that'll allow you to put in the 4th root. Mine doesn't have it. So I have to take this one to the 1/4 power. Which is 1.61 times 10 to the minus 5. There we go. So that's the first one. The second one is 4s cubed. Right? So s cubed is equal to this number divided by 4. Which is 7.5 times 10 to the minus 28, and s then is equal to the cube root of that one. So I'll do, and there we go, 9.09 times 10 to the minus 10. Right? This one is simple. You just take the square root of both sides. So in this case, I'm just going to take the square root of that number. 1 exponent 28 minus 28, and take the square root of it. 1 times 10 to the minus 14. Right? This one is the same. Square root of that number. 6.1, and then the exponent, and then I'll take the square root of it. 7.8 times 10 to the minus 3. This is s. And this one is treated like that one. 27 into this one, then take the 4th root. So I'm just going to do both of those calculations right here. 2 exponent 33 minus sign, and then 27 divided. Then I'll take the 4th root of that. 2.9. Well, let's see, it's only got 2. So 3 times 10 to the minus 9. There we go. And these are all in molarity. All right. Which is the least soluble? Now you can figure it. Now you can compare numbers. I'd look at the exponents first. And if you have 2 with the same exponent, then you go to the coefficient to break the tie. So there, 5, that's a small one. This is the, wait a minute, 10, excuse me. 10, 5, 14. 10 to the minus 14 is cadmium sulfide. Cadmium sulfide should be the least soluble of each one of these. All right, that's how you do it. He's methodical, break it down. Henry Ford jumps in. You do the same thing over and over and over. Okay, I'll scoot that back a little bit. There we go. Check that one off. Now I'm going to go to 13. Here we go. 13. The molar solubility of barium carbonate with KSP 1.6 times 10 to the minus 9 in 0.1 molar calcium chloride solution is. All right. Now it's not just pure water anymore. This is 13. All right. Now we have barium carbonate. That's going to make barium 2+ ions plus carbonate. There we go. All right. So we're given the KSP, and we will need that eventually. But we're also given starting conditions. The starting conditions are not zero anymore. So now we need to use our ice table. Okay? So what is our initial concentration of carbonate? It's 0. What is our initial concentration of barium, though? Barium is 0.1 molar. Okay? Now what's the change? Well, we're going to lose some from this side, and one of these over here, and one of these over here. Well, we don't need this one, because that's solid, right? We need these two. 0.1 molar plus S, and then S. So our expression for the equilibrium is the KSP 1.6 times 10 to the minus 9 is equal to this one times that one, and they're both to the first power. Right? So we can do this one like that. Okay. Now we have to make a decision. Let's see, make a decision. Is this S large enough to be retained in the expression? We'll look at the solubility. How much barium would it produce? Right? This number right here says very minuscule amounts of barium are actually going to be produced. So this is very small compared to that, extremely small. So what we can do is approximate, and now we have 0.1 times S is equal to that number. So this is going to be divided into that one. So S divided into this is 1.6 times 10 to the minus 8. You know, prove it to yourself. Excuse me. Hold on a second. Right. Okay. I was looking for the answer. It's not there. Right. This is the right solubility in that solution, but it's not there. So the answer is none of these. Okay. There's nothing even close, right? So that's 13. The solubility changes if you have a common ion in solution already. All right, let's see. That's good. Okay, that was 13. So let me see, what do I have next? 13, 17. Okay, 17. This is a good one. All right, 17. All right. We have a solution that's 1 molar in hydrogen ions. Okay? 1 molar hydrogen ions. And what we want to know is which of the following salts are more soluble in that solution than they are in water. All right, what do we have to choose from? Sodium chloride, calcium carbonate, potassium chloride, silver chloride, and potassium nitrate. Okay. Remember the lecture discussion. The only types of compounds that are more soluble in acidic solutions, where you have the protons, are those that are composed of an anion that is a strong base. So you find the compound that has a strong base anion in it. All right. So in order to find the strong base, you look for the conjugate acid of that base and see, is that conjugate acid a strong or weak acid? So hydrochloric acid is a strong acid, so that is a weak base. Same here, same here. Both weak, weak, which means they will not react with protons. How about this one? Nitrate, nitric acid is a strong acid, so its conjugate base is weak. The only one that's made from a weak acid is this one. It would be derived from carbonic acid, which is weak. So this is a very, very strong base. This one will be more soluble in acidic solution. In fact, not only will it be soluble, it will produce carbon dioxide gas. This much acid and that calcium carbonate will fizz. Okay, that was 17. 19 coming up. All right. 19. Let's see, scroll down, here we go. Let's see, you have a solution consisting of 0.1 molar chloride and 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise to this solution. Okay. If the KSP for silver chromate is 9 times 10 to the minus 12, and that for silver chloride is 1.6 times 10 to the minus 10th, which of the following will precipitate first? All right. Let's see. Here we go. So here's how we approach this problem. What reaction is going to occur? What is the potential reaction for each one of these? Well, silver nitrate is completely soluble. So you're going to have silver ions in solution at 0.1 molar silver nitrate concentration in the beginning. Okay. You're also going to have an equilibrium established at some point for silver chloride and for silver chromate. So the possibility is this one. Or this one. 2. And then you produce 2 like that. Excuse me. Like that. Okay. So, which one is going to precipitate first? The one with the lowest solubility for, right, solubility of this versus the solubility of that. So whichever one has the lowest solubility will precipitate first. In fact, to answer this question, let's see. We don't even need to know the concentration of silver nitrate. All we need to know is the solubility of each one. So you need to determine the solubility here, which would be what? This would be S, this would be S, this would be S. If this is S, then this is 2S, and that's S. Correct? So this is going to be S squared is equal to the K value, right? S times S is equal to the K for silver chloride, which is 1.6 times 10 to the minus 10. So S is equal to what? Square root of that. 1.6 exponent. There we go. And take the square root. 1.3 times 10 to the minus 5. How about this one? Well, this is going to be 2S squared times S, which would be 4S cubed, is equal to its KSP, which is 9 times 10 to the minus 12. Okay? So we need to divide both sides by 4 and then take the cube root. So I'm going to do that in one series. 9 exponent, 12, change sign, and then 4 divided into that. And then I need 1/3 power. (1.3 times 10 to the minus 4). Molar solubility. So which one will precipitate first? The least soluble silver chloride will precipitate first. That's why the answer is right there. Okay? That's one way to solve the problem. If you have starting concentrations for everything, which we do, then what you can do is calculate the Q for each one and compare it to the K for each one. And see which one is, well, which one will precipitate and which one won't. Actually, this is a better method because what if Q's are both larger than their K's? Then you're going to say they're both precipitate, but we need to put them in order. So that's what this does. The reason we can use solubility here instead of Q values is because they're both at the same concentration. 0.1 molar, let's see, where are we? Yeah, 0.1 molar chloride, 0.1 molar chromate, and 0.1 molar silver nitrate. They're all the same concentration, so we can compare the solubilities and get the answer. If they're different values, then you have to go to calculating the Q. And then you compare the Q's to their K's and see which one is greater in ratio to its respective K. And then you can determine which one precipitates first. Actually, you know, you don't need to do that, because why did it say? 0.1 molar silver nitrate is added dropwise. So that means that one of them is going to precipitate first because you're adding small increments. You're not just dumping the whole thing in there. If you dump the whole thing in there, then probably both of them will precipitate at the same time. But if you add dropwise the silver nitrate, then you will get a sequential precipitation. Okay, that was 19. What's next? Let's see. How am I doing on time? I got till 3 o'clock. Okay. Let's see. The next one I got marked is 21. Let's go ahead and do it. Yeah, it's a little involved, but doesn't mean we can't learn something from it. Correct? 21. I'll write that up there because it might take a lot of room. All right. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar potassium fluoride solution to begin precipitation of calcium fluoride? Right. And it gives you the KSP for calcium fluoride. All right. So, what's the reaction that we're interested in? It doesn't have anything to do with calcium nitrate. Nitrate's a spectator, right? All nitrates are soluble. So nitrate is just going to sit there. It's the calcium ions that are provided by this one. And they're added gradually. How many moles of calcium nitrate? And we have to assume that the addition of calcium nitrate in such a fashion that it will not change the total volume. Because if it changes the total volume, we get a change in concentration. And then we have an issue that can be solved. Don't get me wrong, we can solve it. It's just a little more complicated. But for this problem, we're going to assume that calcium nitrate added will not affect the total volume. Right? So we have 1 liter. That's given. We have, let's see. Yeah, 1 liter of 0.182 molar potassium fluoride. Okay. And we're going to precipitate calcium fluoride. All right. Potassium is a spectator, just as nitrate is a spectator. So what we have is we're forming calcium fluoride. And the equilibrium setup here is between that and this. Right? They're in aqueous solution. I just didn't write it. Okay. So what question do we really need to answer? We need to answer the question, at what concentration of calcium added is the Q equal to the K? Because at that point, you're right on the edge, the cusp of precipitation. Just a little bit more calcium, and you will begin precipitation. And that's what it means right here. Begin precipitation when the Q is equal to the K. All right, so let's set up our ice table. All right, what do we have to start with? Well, we have 0.182 molar fluoride, 0.182 molar fluoride, and we don't have any calcium to begin with. We're going to start adding calcium. So how much do we add? That's the question, right? That solves the problem. How much do you add? How many moles of calcium do we add? And notice, calcium, if we know this one for that ion, we know the moles of calcium nitrate because 1 calcium for every calcium nitrate. It's a 1-to-1 relationship. That's 2. 1-to-1 relationship. So if we know this one, we have answered our problem. So for every one of these, how many of those do you get? Well, for every one of these that we add, we're going to be subtracting 2 of those. Right? Because as we add these, it combines with these, producing that. So the equilibrium situation at the very start of precipitation is this and this, now equal to our K value is 4 times 10 to the minus 11. 4 times 10 to the minus 11 equals this one. Well, actually, if we're calculating the Q, well, the Q is equal to the K, so that's valid. And then we have 2x here squared. Okay, so now we solve for x and we got our answer. So what do we have here? We have 4x squared times x is 4x cubed. 4x cubed. So we need to divide this into that, which would be 1 times 10 to the minus 11, and take the cube root of it. I get 2.15, let's see, 2.2 times 10 to the minus 4. Well, that's molar. Right, that's moles per liter. Well, what's the volume? The volume is 1 liter. So that's also the number of moles. 2.2 times 10 to the minus 4 moles, which is, where are we? Wait a minute. What did I do wrong? Oh, no. I did a serious error. Very serious error. Which means I can't add. 0.182 minus 2x. All right, let's try this again. X 0.182 minus 2x squared. Okay, now we're back on track. All right. So now we have to ask ourselves, is this 2x term big enough to keep? how much of that is going to be required? With a K value of 10 to the minus 11th, that X is going to be vanishingly small. So we can say this is X times 0.182 squared. Okay, so now let's try this again. Square that number and divide it into this number. Four exponent 11, change sign, and then flip it and divide. Okay, so that takes care of that term is now equal to X. That's it. That's the answer. That squared divided into this is equal to X. So that's 1.2 times 10 to the minus 9. Molar of calcium nitrate. Or, since it's 1 liter, moles of calcium nitrate. There it is, right there. Okay? All right, that was 21. 23 coming up. All right, 23. All right. Just refreshing my memory here. 23. Let's move it on up a little bit. Middle of the page. There we go. 23. I better use as much of this space as I can get. All right. We have a solution is 0.01 molar in each of lead 2 nitrate, manganese 2 nitrate, and zinc nitrate. We add solid sodium hydroxide to this solution until the pH of the solution is 8.5. So which of the following statements is true? We're also given the KSPs for each of these solids, because what's going to happen? What's going to happen? When you put sodium hydroxide in there, you're adding the hydroxide anion, which is a very strong base, and which will form insoluble compounds with each one of these cations: lead, manganese, zinc. And that's obvious from their KSPs. If they have very small KSPs, that means that hydroxide is going to latch onto those cations. But what we want to know is which ones will precipitate. Now, this is a case where we are able to calculate the concentrations of the various components in the reaction, calculate the Q value, and then compare the Q to the K. And wherever the Q is greater than K, those salts will precipitate. All right, so let's take them in order. This one, okay, that one does what? Well, it makes this one plus 2 hydroxyls. Okay. The second one makes this. And the third one makes this. All right. So what are the initial concentrations of each? We're interested in this one. What about that one? What is the initial concentration of hydroxyl? Look at the pH. The pH is 8.5. All right. What's the pOH? pOH is equal to 14 minus that. .50. Now, what's the hydroxyl concentration? The hydroxyl concentration is the antilog of the negative. So 10 to the minus 5.50 equals what? Let's try it. 5.5, change the sign, and then take the power of 10. 3.16 times 10 to the minus 6. Okay, so now we know the concentration of each one of these. 3.16 times 10 to the minus 6, each one. All right. What's the concentration of each of these ions? Well, they're all 0.01 molar, right? And it looks like 1 for each one. So this concentration is the same as the formula concentration, which is 0.01. Okay? So now we have values that we can calculate Q, right? This is not equilibrium, right? This is starting position, and we have the values, concentration values, so we can calculate Q for each one. Right? So what would be the Q? It's the same as the K, only without equilibrium values. So it's this one times that one squared, right? 2, 2, 2. Each one of these squared times 0.01. Correct? So it'd be the same for each one, wouldn't it? Because they're each 1 and 2, 1 and 2, 1 and 2. So we just do the calculation once. So we square that one. I've still got it in my calculator, so I'm going to square it. And then multiply by this one, 0.01. 1 times 10 to the minus 13. All right. Now what we have to do is compare the K's. I didn't write the K's up there, did I? All right. The K for this one is equal 1.4 times 10 to the minus 20. The K for this one is 2 times 10 to the minus 13. Yep, 2.0. And the K for this one is 2.1 times 10 to the minus 16. All right. So which one is the Q greater than the K? This one's bigger than that one, right? So this will precipitate. This one is less than that one, right? 1 versus 2 times 10 to the minus 13. So this one will not precipitate. This one, that is greater than this. That one will precipitate. So lead and zinc are the only two that will precipitate. Let's see, which one is that? D. Only zinc hydroxide and lead hydroxide will precipitate. All right, that was 23. Hold on a second. I'm gonna let my cat out.
Come on, Nancy. Come on, Nancy.
There you go. All right. Wet my whistle. All right, I've got also 24. Oops, too far. So 24. Need some space. Okay, so let's do that. This. There we go. 24. All right, what does 24 say? In the qualitative analysis scheme for metal ions, how are the analytical group 2 cations separated from cations of the third and fourth, and third through fifth? All right, so you need the that flow chart, and I don't have it ready to share. It might be, yeah, it's in this document. So let's scroll down. We'll come back to 24. So let's scroll down. In the qualitative, let's write what we need up here. In the scheme, how are the group 2s separated from the 3s through the 5s? Group 2s separated from 3s through the 5s. Okay. So let me scroll down to the end of the document, and this will also be useful information that you can access before you open up the lockdown browser. Be sure and print this out. It's in there in the same folder with the exams. So be sure you have this available. Otherwise, you won't be able to answer the question unless you have it memorized. So how do we separate group 2s? Well, group 1s are separated out by simple acidification with HCl. Then group 2s are separated out here like this. Notice what's common to all of them. Sulfide, 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 sulfide. We add hydrogen sulfide. And that separates out group 2 from everything else. All these others are left behind. So simply add hydrogen sulfide. So let's go back up to 24. There we go. Right there. Okay. So which one is it? By addition of HCl? No. No. H2S in acidic solution, forming insoluble metal sulfides. Now this, adding H2S in acidic solution, it doesn't matter where the acid comes from. But if you're going to follow the sequence, that acid needs to be HCl. Why is that? That's because the group 1s are all chlorides. So HCl is the acidifying agent prior to adding H2S. Right? So technically that statement is true, but it leaves out one tiny detail. It leaves out the chloride. Okay, so that answers 24. All right, let's see, 25, how about that? 25, here we go. Which of the following solid salts should be more soluble in 1 molar ammonia than in water? All right. Let me see if this marker's got any life left in it. All right, so these salts, sodium carbonate, potassium chloride, silver bromide, potassium nitrate, and none of these. And we want to see which one is more soluble in 1 molar ammonia. Okay, what are we talking about here? Well, if you add ammonia to a solution of those former, let's say, lead, what were they? Let me back up. Lead, manganese, or zinc, then the ammonia is going to release hydroxyls. And you may eventually get enough hydroxyls to precipitate those, but that's not what we're talking about here. Like, none of those are in here. None of those. Sodium hydroxide is soluble, potassium hydroxide, even silver hydroxide is soluble. Potassium hydroxide is soluble. So we're talking about something else. In fact, we're talking about complex ion formation. And how do complex ions form? Well, first you need, ammonia has to be a Lewis base. It has to donate a pair of electrons in order to become a ligand in a complex ion. Right? So what does that mean? That means you need a Lewis acid to react with it, an electron acceptor. Right? None of these anions are candidates, right? They would be Lewis bases. This Lewis base has to react with one of these metals. So which ones will it react with? Well, that's an alkali metal, that's an alkali metal, that's an alkali metal. No alkali metals form complex ions. They're predominantly transition metals. And there's only one transition metal in that group, silver. So that's why the answer is silver bromide. That makes the compound more soluble. Why? Because if you form the complex ion, a stable complex ion, then you remove, look like this. If you form a complex ion here, then you remove silver. And Le Chatelier says when you remove that, you're going to shift the equilibrium to the right, which means you make it more soluble. Okay, that was 25. Let's see, 27, the next one on my hit parade. There we go. In fact, 27 might be a backtrack. Let's see, get another marker. 27, the correct mathematical expression for finding the molar solubility of barium chloride. Right. So we did one like this before. You need to be able to write barium chloride. Barium, which is an alkaline earth. That means 2 chlorines. So this solid has limited solubility to produce barium 2 plus 2 chlorides. There we go. Out. Yeah. All right, so what's the expression? What would be the equilibrium solubility product expression for this right here? Well, if this is S, if we're losing some of that, that means we're going to get one of these for every one of those. You get an S there, and you get two S's here. Okay? So that means KSP is equal to that S to the first power, and this S, this 2S to the second power. So what does that mean? That means 2 squared is 4, S is squared. 4S squared times S is 4S cubed. So KSP equals 4S cubed is the answer to this one. Right there. Okay? 27. All right. Uh, 30. Let's see if 30 is challenging. 30 is a definition, right? Which is good. It's kind of like taking a break. Do you know your definition? So 30 wants us to, which of these comparisons leads to a precipitation? And I've mentioned it before, but we'll say it again. Calculate the Q for the actual concentrations of your cations and anions, and compare it to the K solubility product for those two, cation, anion. If the Q is greater than the KSP, then you will get a precipitate. Right? That's why C is the answer. That's definition. All right. Let's see. 34 I've got marked off on my list. Oops, too far. There we go. 34. Okay. We can handle this one. 34. Let's see, am I still on screen? It's walking a little bit, isn't it? There we go. 34. Calculate the solubility of silver chromate in a 0.049 molar silver nitrate solution. All right, so do we have a common ion here? Yes, we do. We have silver. Silver is common in this solution to the solid that we're attempting to put in solution. So what do we got? We've got silver, 2 of them, and then chromate. Actually, I don't need that parentheses, do I? Right, that solid makes 2 silvers and 1 chromate. All right. Come on. All right. Okay. So what are the other conditions? 0.049 molar silver nitrate. All right. Silver nitrate is completely soluble. And for every 1 formula here, you get 1 silver. So that is the starting concentration for silver. Is 0.049 molar. Chromate is 0. Okay, what kind of change are we going to get? Well, we've got nothing here, so it has to go that way. So we're going to get something over here. And for every one of these, we get 2 of these. Correct? So now, let's see if I can add this time. 0.049 plus 2x, and this is x. So let's look back at the question. Calculate the solubility. Well, is x the solubility of that compound? Or we could have called it S. For every one of these, it came from one of those. So X is the solubility of that compound. So we can solve for X, and that's our answer. All right. So what is the solubility product for that? 9 times 10 to the minus 12. 9 times 10 to the minus 12 equals this one squared times this one to the first power. Now we have to ask ourselves, do we need to keep that 2x? With a solubility product that low, that 2x is going to be insignificant. So we can say, no, we don't need to keep that. So now all we have to do is square this number, divide it into that number, and we have our x. So 0.049 squared divided into 9 times 10 to the minus 12. .7, let's see, 3.75 times 10 to the minus 9. Molar. So let's see, is that one of the answers? Close enough, right there. Right, right there. It doesn't want to behave, does it? There. 3.7 times 10 to the minus 9 is 34. Okay, moving on. 36. Let's see, we put it right up there, 36. All right, 36. How many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? Okay, we have a common ion, the fluoride. Right? So we have to do our ice table, and let's just set it up. Calcium fluoride looks like this, and it's going to produce calcium plus 2 fluorides. Okay. So what's our initial concentration of fluoride? 0.089. And since the ratio is for every 1 mole of these, you get 1 fluoride, that is the concentration of the fluoride ion, 0.089 molar. 0.089 molar. You have none of this, right? So the change is you're going to get some of this. That's 1 and that's 1. So let's use S here. This is going to be plus S, and this is going to be plus 2S, right? 2 to 1. 2 to 1. So now we have S here, and we have 0.089 plus 2S. Right? So our expression will be, we need the K value. 4 times 10 to the minus 11. 4 times 10 to the minus 11 equals S times 0.089 plus 2S squared. All right? So the same question pops up. Does 2S deserve to be included? With a 10 to the minus 11th K, 2S is going to be insignificant. So we can drop that out, and we just say this squared divided into that is equal to S. 0.089 and square it. And then divide it into this one. 5. Let me do that again. I'm not comfortable. 0.089 squared, and then 4 exponent. Okay. 5. Let's hang on to a decimal for now. 5.05 times 10 to the minus 9. And that's molar. What was the question? The question is, how many moles of calcium fluoride will dissolve in 3 liters? This is how many moles in 1 liter. So if you have 3 liters, that tells you the number of moles of calcium fluoride. So I'll round this one off. Let's see. What can I round it off to? 3 liters. Okay, that's 2 significant figures. So I got to round it off to 1.5 times 10 to the minus 8. Moles of calcium fluoride. Okay? And it looks like it's this one, 10 to the minus 8 right there. Okay? That was 36. All right. It's still on screen. Yep. 37. All right, we stay right where we are. What is the best way to ensure complete precipitation of tin sulfide from a saturated H2S solution? Well, let's look at it this way. SNS, tin 2-sulfide, is what we're trying to precipitate. And assume that that's it, that's all there is. That's all the tin. There's tin in solution. And we're going to precipitate it with sulfide. Right? What's the best way to make sure that all of that tin gets precipitated? You want to produce as much sulfide as possible to drive the reaction back here. So how do you increase the amount of sulfide in a solution that is saturated at H2S. Right? And these are aqueous. In fact, all of them are aqueous. Right? How do you secure the maximum amount of sulfide out of this so that it can react over here and drive that reaction back? These are coupled reactions. We want to maximize that. How do you do it? You remove as much hydrogen from this reaction environment as possible. And the best way to do that is with a strong base, like right? Add base, remove that, drive the reaction this way, provides plenty of this, goes back that way. So the answer is add a strong base. Okay, and that's why that you need to add the strong base. It doesn't have to be hydroxide, but that's a good choice. It's cheap, and the product is water, so it doesn't interfere with anything else. So that's the way I'd do it. Let's see, that was 37. Sorry, I didn't write it up there. 37. All right, 37. Let's see, next page. 40. Okay. Moving right along. Trying to keep up with my hard copies here. All right. Scroll down to 40. Here it is. All right. We're given the concentration of magnesium in seawater is 0.052 molar. At what pH will 99% of the magnesium be precipitated as the hydroxide? All right. So, what's the precipitation reaction going to be? Well, if we're going to have hydroxide, then we have to have a pH that's high enough to deliver the hydroxide. Okay, so the reaction is going to be aqueous. And this is going to be 2 hydroxyls. There we go. And the equilibrium expression is going to be KSP is 8.9 times 10 to the minus 12. And that's equal to magnesium times hydroxyl. Yep. Squared. All right. So if yeah, okay. I'm just thinking for a second. What's our starting concentration of magnesium? Well, the starting concentration is 0.052. Right? But the conditions of the problem say we only want 99% of that to be precipitated, right? So we really only need to start with 0.99 of that because we don't care about the other 1%. So this would be times 0.99, 99%. Right? So 0.052 is 5.148 times 10 to the minus 2. Initial. 5.158, did I say? 10 to the minus 2. 148, excuse me. There we go. Molar. All right. And the concentration here is unknown. Right. But it's going to be, well, let's see, we're not looking for solubility. We're looking for the concentration required. So this fits into here, whatever it happens to be, is the concentration of hydroxyl. Right, so this value over here is 8.9 times 10 to the minus 12 equals this one, 5.148. Actually, that's not, shouldn't use brackets. It's not equilibrium yet. 10 to the minus 2 times x squared. All right. And that will give us the hydroxyl concentration that's required to perform that precipitation. So what is x? Well, x is this one divided into that one, then take the square root of it. So 8.9, 10 to the minus 12, and divide by 5.148, 10 to the minus 2, and then take the square root. So 1.315 times 10 to the minus 5 is equal to the hydroxyl ion concentration. So the question is not that. The question is, at what pH would give us this much hydroxyl concentration? So we can calculate the pOH, right? Just take the negative log of that value. And that gives you the pOH. 4.88. pOH equals 4.88. pH is equal to 14 minus 4.88. Let me do that again. There we go. 9.12. 9.12. That would be the pH right here. Okay? That was number 40. Let's see, we're coming down to the wire. 2:45. Yep. Coming down to the wire. I might run over a little bit, but that's all right because there's nobody here but me. All right, let's see. Scooch that back a little bit. There we go. All right. That was 40. 41. 41 looks like trouble, doesn't it? Maybe it is and maybe it isn't. All right, let's see what the question is. A solution contains 0.018 moles each of iodide, bromide, and chloride. Each one of those at that many moles. When the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates? All right. The nice thing here is that you've got the same number of ions produced for each one. So that means we can compare the Ks and determine which one precipitates first. All right, so the first one that's going to drop out is silver iodide at 10 to the minus 16. Silver bromide next, silver chloride last. So how much silver chloride precipitates out? Well, you've got to go through a sequence. You got to say how much of this, we've got to remove all the iodide first with silver, and then the silver left over has to react with bromide and remove it, and then any leftover silver can react with chloride and remove it. Okay, so we've got to do a sequential calculation here. All right, so how much silver do we start with? That's important. Let's see. Here it is. 200 milliliters times 0.24 molar. Let's see, this is 41. 200 milliliters is 0.2 liters times 0.24 molar. And remember, molarity times volume equals moles. So we'll do that calculation. That should be 0.048. Yeah, 0.048. 0.048 moles of silver to start with. Okay, the first one that's going to precipitate is iodide. Right. So we'll take this many moles, and since they're 1-to-1, equal number of silver is required. So the iodide is 0.018 moles, right? It's going to remove 0.018 moles of that as silver iodide. Let's see, that's not right. This one, silver iodide. What's left over is silver ions. So that would be 0.030. And this is moles. Right? Next is what? Well, next we're going to remove silver bromide. So minus 0.018 silver bromide. Right? So that's 2, that's 1. So that's how much silver is left over after silver bromide. Actually, that's there. So now we're down to the last amount of silver, and how much, let's see, 0.018 moles of chloride, right, is too much. This is the limiting. Silver's limiting. So you're only going to get that many moles, right? That's all the moles you're going to get. And you're going to have some chloride left over, right? Subtract that, you're going to have 0.006 moles of chloride left over. but you will get this much. Let's try another one. You will get this much silver chloride. Okay? So back to the question. How much silver chloride precipitates out? And we look at the answers in grams. It's not moles. Right? So we got to convert that many moles to grams. Right? Multiply this one times that one. Cancel the moles. So what's the molar mass of silver chloride? Well, let's see, I have to look it up. Silver is, let's see, silver is 107.87. 107.87. And chlorine is 3545. So that's 142.32. 142.32 per mole. And multiply that times 0.012. 0.012. 1.7 grams of silver chloride will be precipitated. That's right there, B. Okay, that was 41. Let's see, 43. Oh, we got another sequential precipitation question. Here we go. 43. All right. So what are they looking for? 43. When a mixture containing cations of analytical group 1 through 3. Okay, so we've only got the ones in group 1 through 3, not all of them. When that mixture is treated with H2S in acidic solution, which cations are expected to precipitate? Right. So we are given cations in groups 1 through 3, and we're going to treat them with acidic H2S. And I am going to say this acidic is HCl. That's important. Okay, now let's go to the back of go to our diagram, our flow chart, and say which cations are expected to precipitate. So let's go back here, here, and here. So groups 1, 2, and 3, right here, only have these chloride groups of cations, and these groups 3 and these groups 1, 2, and 3. These right here. Okay. If we acidify, what are we going to get? Right. Well, these were up there, so we acidify and we get the chlorides. So we get group 1, correct? Group 1, and then we add H2S and we get group 2. That's it. Group 3, we can't get group 3 until we add carbonate. Until we add base. Okay? So now let's go back up to 43 and answer the question. Let's see, right? There it is. So we only get group 1 and 2. 1 and 2 only, right here. Okay, that's it. That's D. All right, 43, 46. 46. There. All right. So we're told that we have this reaction. We're forming a complex ion with this M2+, this metal. That's what M stands for. This metal with a 2+ charge combines with ammonia. First step, adds one ammonia. Second step, adds another one. Third step, adds a third one. Okay? And notice the K values for each one of these is heavily weighted toward the right, which means you're forming mostly of this, but even when that's formed, this reaction takes nearly all of that and shunts it over here to this one with that K value. And then this one, that one then picks up another ammonia and ends up over here with that K value. Okay, so let's look at the what's given. A 1 times 10 to the minus third mole sample of MnO3 2. 1 times 10 to the minus third moles sample of MnO3 2 is added to 1 liter of 15 molar ammonia. Okay? What's the dominant species in this reaction? All right, there's a lot of extra information in here that you really don't need. How do you tell the dominant species? Well, you look at the sequence of reactions. Each one is weighted heavily toward products. So that means as this one forms, it's picked up by this one. As this one forms, it picks up by that one. So the dominant species is the last one in the sequence. Because each time you produce one over here in massive amounts, it ends up as a product in this one. And then that one ends up as a product in this one. So the dominant species is the final product. Right there. That's why the answer here. So really, that's a thought problem. You didn't have to do any calculating. I mean, you could. You could calculate each of the components here. Let's see. You could even combine these equations into the overall equation. And notice that this one would cancel this one, and this one would cancel that one. So you'd really have M2 plus 3 ammonias yields this final product. And then what's the K value? Well, the K value is K1 times K2 times K3, which was 2, 4, 7, 10 to the 7th. So the overall K would be 10 to the 7th, which means definitely that's the major species. All right. So that was 46. Yes. Let's see how we're doing on time and problems. I've got 1, 2, 3, 4. 4 more to go. Okay. I'm about out of time, but I'm going to keep going. I want to get these done, because each has its place in explaining what's happening in solubility and complex ion formation. All right, for this one, 47. What is the concentration of nickel ion in a 0.045 molar nickel nitrate solution that is also 1 molar ammonia? And the K of formation for nickel hexaamine nickel 2 cation is 5.5 times 10 to the 8th. All right. So what are we given? Well, we're given a nickel nitrate. Let's put it over here on the side. 0.045, 0.045 molar nickel nitrate solution, and 1 molar ammonia. All right. We're also given the formation constant. We can look at that when we need it. Okay, so first thing is, what reaction are we interested in here? The question is, what's the concentration of nickel? So are they saying that all of the nickel is not converted? We're forming a complex ion here, right? So the reaction then is the nickel 2+ ion formed from this compound. All nitrates are soluble. And then we're adding ammonia. And the complex is going to give us 6 ammonias. There, like that. So we'll have nickel, and we'll have ammonia, 6 of them, with a 2+ charge. And this is the aqueous. Okay. So that is balanced. So this problem, I think, would be worked better if we do stoichiometry first, followed by equilibrium. Okay, so let's say, what are we given to start with? We're given 0.045. Since there's 1 nickel for here for every 1 there, this is start 0.045 molar. Okay, and this is 1 molar. All right. Of course, this one's 0. So what's going to happen? Well, the stoichiometry finish is all of this is used up. Correct? All of that is used up. And this one is going to be 1 minus 6 times 0.045, which is equal to what? Let's go ahead and calculate it. 0.045, enter 6 times and subtract that, which is 0.27, subtracted from 1. 0.73. Ammonia is left. And now, how much of this did we produce? Well, 1 of these for every 1 of those, right? So we have 0.045 molar. Okay, that's the stoichiometry part. Now we can do the equilibrium, I think. Yeah. Okay, so now we're going to do the equilibrium. Initial now is 0. We used it all up. 0.73 molar is the ammonia concentration for equilibrium. What did I say, 7.3? Yeah, 7.3. And then 0.045 molar for the complex ion. Okay, what's the change? Well, there's none of that, so it has to move back this way, doesn't it? Right? So there's 1 to 1. That means if this one shows up, then this one has to lose some. How much does this lose? Well, actually, it gains some, right? You take this and disassociate it, you get some of this, and you get 6 of those. So the equilibrium expression for this formation is X here, 0.73 plus 6X here, and 0.045 minus X there. That's our equilibrium expression. Okay, I'm just checking my math. All right. Now, I didn't talk about it earlier, but this is a good X to have. If we solve for X, then we have answer to the question, what is the nickel concentration? So that was fortunate that we chose X that way. Now, what's the expression? Well, I'm going to have to make some room here. So let's erase this part, at least until we get the equilibrium expression written. So what is the equilibrium expression? Well, it's got a value, 5.5 times 10 to the 8th equals this term to the first power divided by this term times this term to the 6th power. Okay? Now we just plug in some values here. So this one is going to be 0.045 minus X equals okay. This one is going to be X. And this one is going to be 0.73 plus 6X to the 6th power. Okay, now that I got all these numbers in the expression, I'm going to erase this. All right. So now we've got to make a decision. Are these X's worth keeping? Well, let's see. Do we need to throw both of them away? We could just throw this one away because it's to the 6th power. But if it's that small, it shouldn't matter to this one either, right? Because this 10 to the 8th means it's over here to the, let's see, 8th power is just short of 1 billion times. It's a half a billion. Half a billion times favors this. So that value is going to be almost nothing compared to these values. So I think we can say 5.5 times 10 to the 8th equals 0.045 divided by x times 0.73 to the 6th power. So we just put x over here, put this number down here, and that's our calculation. So I'm going to do the power first. 0.73, enter, to the 6th power. And then I'm going to multiply it by this one. That's my denominator. Now I punch in the numerator and divide by that denominator, which is 5.4 times 10 to the minus 10. Now let's see if I got anything close to that. Yeah, there it is right there. That's the concentration of nickel ion that's left in solution, right? Very small amount, right? So the creation of this complex ion was almost complete. All right, that was 47, and I'm 8 minutes over, which is all right, I guess, considering. Let's see. 50. I want to do 50 next. Oops, too far. There we go. All right. This one's about dead too. Let me see. Let me get a fresh cloth. There we go. Rice is better if it's fresh. All right. So 50. The Kf for the complex ion, diamine silver 1 ion, is 1.7 times 10 to the 7th. The KSP for silver chloride is 1.6 times 10 to the minus 10th. Calculate the molar solubility of silver chloride in 1 molar ammonia. All right. So we need the molar solubility, that is, what is S, of silver chloride in 1 molar ammonia. All right, what equations are operating here? We have 2 of them. One is the formation of the complex ion, right? So we have silver plus ammonia. Actually, there are 2 of them. And that forms silver and this one plus charge. There we go. And that K value is 1.7 times 10 to the 7th. Formation. Okay. We also have silver chloride. We're going to precipitate. We have the desire to discover silver chloride solubility in this solution. So we have silver chloride solid, which would dissolve as silver plus chloride. Oh, and that's solubility product is 1.6 times 10 to the minus 10. Okay. So the first thing to recognize about this, I haven't put the concentrations in yet, is that both of these reactions are occurring in the same environment. They're in the same solution, or they're trying to get into solution. So an overall equation would be perfectly valid. We could combine these. We can combine these. And let's see. Yep. So what would happen if we combine these two equations? Right? We have to do something with the K's, right? What do we do with the K's? If we combine these reactions as they are, without any modifications, then we multiply those two together, correct? So this would be silver chloride solid plus silver ions in solution plus 2 ammonias in solution. And then on this side we have the complex ion, and that's in solution, plus silver plus chloride. And those are both in solution also. All right. So now what do we do to simplify? Well, we look. There's silver, there's silver. Cross it out. Anything else? No, that's it. Okay. So what's the KEQ? Right? The KEQ would be the combination of those two. We have to multiply them together. 1.7 to the 7th power, is that correct? Just checking. Yes. Times 1.6, 10 to the minus 10 power. So I get 2.72 times 10 to the minus 3. 2.2 times 10 to the minus 3. That's the KEQ. All right. So now that we have this expression, what is that KEQ equal to? Well, it's equal to this one times that one divided by this one. Oh, no, that's a solid. So it's only divided by this one squared. Right? So that KEQ, I'll just write it over here, is equal to this term times this term divided by this term. There we go. Oh, and that's equal to 2.2 times 10 to the minus 3. All right. So now we got that much done. So if we're going to put this in solution, if we take some of that out and put it in solution, where's it going to show up? Well, it's going to have to subtract 2 of these, right? Right? For each one of these, you have 2 of those. And then for each one of these, you get 1 of these and 1 of those. So there's your terms. Well, that one doesn't count because it's a solid. So if we plug these values in to that expression, we should be able to determine the solubility of silver chloride in this solution. So this would be 2.2 times 10 to the 3rd equals this term right here, S, and then chloride is also S, and then divided by no, excuse me. I'm not finished yet. This is the change. Right, this is the change. What was the initial? Initial concentration of ammonia was 1.0, wasn't it? Yep, 1.0 molar, right? And these are change of plus S and plus S. So the equilibrium values are going to be 1 minus 2S, and this is S, and this is S. So now we can write our expression. All righty. So now we have 2.2 times 10 to the minus 3 equals this one times this one divided by that one. Okay. Now we have to decide, excuse me, that's squared. Now we have to decide what to do with that 2S. Right? Is it going to be large enough that we cannot ignore it? Well, it may not matter. Notice what we have here. S squared over 1 minus 2S squared. So what is that also equal to? That's equal to S over 1, right? That's mathematically permissible. That's squared, so the square can come out, factor out. So that means that this term right here, I'm going to put it down below. I don't want to erase the formulas yet. The reactions. So now bring this down. This is now S. Get a fresh one. I hope it works. Okay, that's now S over 1 minus 2S is equal to the square root of this number, right? We took the square root of both sides. Okay, so what's the square root of 2.2 times 10 to the minus third? Is that right? 2.2 times 10 to the minus third. Let me check that again. 1.7 exponent 7 and 1.6 exponent minus 10. No, it's 2.72. I thought that looked funny. This is 2.72. 2.72 2.72 times 10 to the minus third. Now we'll take the square root of that. Right? So that expression is 5.215 times 10 to the minus 2. So that's equal to this. So now what do? Well, we have to multiply this times that. So that's going to be 5.215 times 10 to the minus 2, because that's 1. And then minus 2 times that times S. 1.04 times 10 to the minus 1. 1.04 times 10 to the minus 1 S equals S. So we got to add this to both sides. So this is 0.104, right? So this is equal to 5.215 times 10 to the minus 2 equals 1 plus this is 1.104 S. Now S is equal to this one divided by that one. 1.104 divided into 5.215 exponent minus 2. And we want to divide 1.104. So S is equal to 4.7 times 10 to the minus 2. Right there. Okay? I'm glad I caught that mistake early. Did all these calculations with the wrong number. Okay. We ought to be getting close. We're already 25 minutes over. All right. Keep going right here, right here, right here. Boy, that marker wants to stick. All right. So let's position it back there. And what's next? Let's see. Let me cross that one out. And we got 2 more. 52. Okay. Let's see. This one's similar to the one we just did, but I might as well do it. Okay, we're identifying this as a system of 500 milliliters of 0.02 molar manganese nitrate mixed with 1 liter of 1 molar sodium oxalate, C204, right? C204. Yeah. Oh, there it is right there, the oxalate ion. C204 is the oxalate ion, which is, it's missing its charge, right? It needs It needs 2 minus. There we go. So let's save that. There. That was a boo-boo. It acts as a ligand to form a complex ion with manganese with a coordination number of 2. Coordination number of 2 means there are 2 of them, right? So for this one, that's the first step. Actually, There's something wrong with this problem. Either, well, no, they neutralized. Okay, manganese 2 plus, oxalate 2 minus. Okay, we got that one. All right, so that's K1. All right, okay. Maybe it's not bad after all. And then this expression gives you the coordination of 2. Okay, I see the problem. This one is flipped. And that number, this K value, applies to that direction. But in order to complete the formation of the ion, this one needs to be inverted. And the K also needs to be inverted. Okay. So find the equilibrium concentration of manganese C204. Okay. So that's the intermediate step. All right. In that case, what we need to do is combine these two equations. That's the first step. Right? So we got the first one, Mn2 plus C2O4 2 minus yields Mn C2O4. Right? These are all aqueous solution. And the K value here is 7.9 times 10 to the third. 7.9 times 10 to the third. Now, if we invert that one that I've highlighted in blue, we should get this one, Mn C2O4 plus C2O4 2 minus yields Mn C2O4, and that's twice with a 2 minus charge. Right? But the K is going to be the inverse of 1.6 times 10 to the minus 2. So that's 1.26 exponent minus 12, minus 2, excuse me, minus 2. And then we invert that. 7.94 times 10 to the first. Right. So if we combine these two, notice this one's over here and that one's over there. That cancels. So our overall equation is going to be Mn2 plus 2 of these and then our product. And the K value is going to be that one times that one. .27 times 10 to the fifth. There we go. Okay. So now that we've got our operating equation, we're looking for the concentration of, well, you know what? Manganese, it's looking for this one that we just crossed out. So once we've solved this one, we've got to take that information and go back up here and solve for the rest of it. Okay. So what's our starting concentrations for these components? How about manganese? The manganese, let's see. The manganese starting concentration, we begin with 0.02 molar manganese, because it's 1:1, times 0.5 liters gives us the number of moles. So the starting concentration of manganese is equal to 0.5 times 0.02. That's the number of moles, but what's the volume now? We added two solutions together, 500 milliliters plus 1 liter. So that's 1.5 liters. So our starting concentration of manganese is 0.5 times 0.02 divided by 1.5 is 6.67 times 10 to the minus 3. Molar. Okay, what else are we given? We're given the oxalate ion, right? So for each one of these, you get one oxalate. So 1 liter times 1 molar is 1 mole. Is 1 mole divided by 1.5 liters. So 1 divided by 1.5 should be 1/3, I think. No, it's 2/3. Is 0.667 molar. Okay. Now we've got our starting concentrations before any reaction. Now, after the initial reaction, this is going to be the stoichiometry. So for the stoichiometry, we start off with this here. Start is 6.67 times 10 to the minus 3 molar. And this is 0.667 molar. So what happens? Well, stoichiometry says all of this is going to be used up. So this is going to be 0, and we subtract minus twice that. Okay, so now the stoichiometric concentration of oxalate is, let's see, let me see if I can, times, subtracted from 0.667 is 0.653. Okay, and in the process, we produce an equal amount over here. 6.67 times 10 to the minus 3 molar, because there's one of those, one of those. Okay, so this is our starting place for the equilibrium. Oh, okay. We've got this value for that concentration. I'm going to write it up here because I got to erase this. So 0.653 molar right here, 0 here, and this one is 6.67 times 10 to the minus 3. All right. So now go back to this expression because we're looking for this concentration right here. Okay. So 7.94 times 10 to the first right there is equal to this one divided by this one times this one. Right? So this one is that value, 6.67 times 10 to the minus 3. This one is unknown. And this one is 0.653 molar. So now we can solve for the equilibrium concentration. That should be S. That's not solubility. That's X. And that will give us this concentration right here. So I need that one times this one divided by that one. No. I need to bring this one over here and say this one divided by that one divided by that one. All right, 1.29 times 10 to the minus 4. Molar. Well, round it off. 1.3 times 10 to the minus 4. Boy, that was a lot of work. And we've got one more. And let's see if this one's going to be as much trouble as that one was. We shall see. 53. All right, 53 wants to know what's the molar solubility of lead-2 chromate in 0.055 molar sodium thiosulfate. Okay. So we've got two equations that have to be combined. The first one is this one. 53, is it? Yeah, 53. The first one is this one. Okay, and that one has a KSP of 2 times 10 to the minus 16. All right, the other one is there. Is this one. Here we go. And that K value is 2.2 times 10 to the 6th. And that's the K of formation. All right. Now, if we combine those two, we get plus. We get lead 2 chromate, which is a solid, plus this one, plus this one, like that. Okay, we've got this on both sides, here, here. And then what's the K for this one? It's this one times this one. So 2 minus 16 and 2.2 to the 6th yields 4.4 times 10 to the minus 10. All right. Now, this is a solid, so it doesn't count. So our initial concentration here of the thiosulfate ion is 0.055. There it is, S2O3. 0.055. Molar. All right. And we've got none of this and none of that. So what's the change? Well, we've got none of that, so we've got to lose some of this. And the question then is, what's the molar solubility of this? So if this is S, this would be minus 3S. Right? It's going to take some of that and put it over here. And for every one of these, you get one of these. And you get one of these. Right? So the equilibrium situation is this, 0.055 minus 3S. This is S, and this is S. Okay, now all we have to do is, let's see, what am I going to do? I'm going to need this space, so I'm going to have to erase that. All right. So this one is going to be that value, 4.4 times 10 to the minus 10 equals this one times this one divided by this one, cubed. Oops. Right? Because of the coefficient, that has to be cubed. All right, so how are we going to solve that? Well, this is going to be extremely small based upon that value, right? So we can count that out. So we just need to cube this one, multiply it by that one, and take the square root. 0.055 cubed. And then multiply it by this one, right? And then take the square root of it. So I get 2.7 times 10 to the minus 7. Is the molar solubility of lead 2 chromate in 0.055 molar sodium thiocyanate, sodium thiosulfate. All right. And there it is right there. Okay. All right. I'm an hour over and I got to be someplace else, so we're going to call it quits. And next week we'll have, well, by midnight next Friday, deadline for this exam, and we'll jump into the chapter on entropy. All right, so stop the share and we'll say goodbye.